Good evening, students. Today let's have a look at the last set of problems on limits and continuity. Let's go to the next question. Next question, please. Question 66. Limit x tends to 0, 3 sin x minus sin 3x divided by x into tan square 2x. Limit x tends to 0, 3 sin x minus sin 3x divided by x into tan square 2x. If I directly apply the limit, sin 0 is 0, here also 0, numerator is 0, denominator also 0. So if it is 0 by 0 form, then generally we go for L-Hospital's rule. But however, in this case, L-Hospital is not advisable because you have x into tan square 2x in the denominator. When we differentiate it, we have to use product rule, so it takes more time. Instead of that, I use a formula for sin 3x. As we already know that sin 3x is nothing but 3 sin x minus 4 sin x divided by x into tan square 2x. Okay, that's equal to limit x tends to 0. Now here on simplification, this will give you 3 sin x minus 3 sin x plus 4 sin x. 3 sin x gets cancelled. So we will have 4 sin cube x divided by x into tan square 2x is there. So when you have tan square 2x here in its denominator, we would like to have 2x whole square. Okay, so I will multiply and divide by 2x whole square. The reason behind it is that as x approaches 0, tan square 2x divided by 2x whole square becomes 1. This expression will become 1. So then you have limit x tends to 0, 4 into sin cube x divided by, now what is remaining in the denominator? Here there is x and here we have 2x whole square. 2x whole square is 4x square. 4x square into x will give you 4x cube. That's equal to 4 gets cancelled. As x approaches 0, sin cube x by x cube, obviously it will become 1. So 1 is the answer, which is the second option. Okay, next question. Limit x tends to 0, e power x minus e power sin x divided by x minus sin x. E power x minus e power sin x divided by x minus sin x is equal to e power x minus e power sin x divided by x minus sin x. Now if I directly apply the limit, I am going to get e power 0, which is 1, minus e power sin 0. Sin 0 is 0 and e power 0 is 1. So here you will have 1 minus 1, 0. Denominator also 0 minus 0 is 0. 0 by 0, an indeterminate form. Okay. So we can go for L-Hospital's rule, but instead of that, what I do is I will take e power sin x as a common factor here. Between the two terms, I will take e power sin x as a common factor. Then what will remain here? Here we will have e power x divided by e power sin x. E power x by e power sin x is nothing but e power x minus sin x minus 1. Did you understand this step? See, I have taken e power sin x as common. So if I take e power sin x as common, in the first term you will have e power x divided by e power sin x. Second term will be 1. Okay. Now if I take this e power sin x inside, as you will observe, e power sin x gets cancelled. Here we will have minus e power sin x. So we will get back to that. And now e power x divided by e power sin x. I am writing that as e power x minus sin x. E power x minus sin x minus 1. Divided by, in the denominator we have x minus sin x. Earlier also we had solved one problem of the same type, but you might remember. Okay. See, now I would like to use this formula. Limit x tends to 0, e power x minus 1 by x. Limit x tends to 0, e power x minus 1 by x is equal to 1. It's a well-known formula. So I am using that formula. In place of x here we have x minus sin x. Similarly, in the denominator there is x minus sin x. Now x tends to 0. When x approaches 0, x minus sin x will also approach 0. So this factor, this expression will be equal to 1. what about this expression? As x approaches 0, this will become sin 0. Sin 0 is 0. E power 0 is 1. 1 into 1. That's equal to 1. 1 is the answer, which is the third option. Then, 70th question. If f dash of 0 is equal to 3, then limit extends to 0, x square by f of x square minus 6 into f of 4x square plus 5 into f of 7x square is equal to limit extends to 0, x square divided by f of x square minus 6 into f of 4x square plus 5 into f of 7x square. Okay. Directly if I apply the limit as extends to 0, let's see what happens. In the numerator we get 0. In the denominator f of 0 minus 6 into f of 0 plus 5 into f of 0. Observe the denominator here, f of 0 minus 6 into f of 0 plus 5 into f of 0. So f of 0 plus 5 f of 0 will give you 6 f of 0. 6 f of 0 minus 6 f of 0, it becomes 0. Numerator is 0, denominator is 0. So now let us go for L-Hospital's rule. So if I use L-Hospital's rule here, limit extends to 0, numerator is not a problem. Derivative of x square is 2x, you don't have any doubt there. Look at the denominator, f of x square is there. I want to differentiate. See, derivative of f of x is f dash of x. So derivative of f of x square would be f dash of x square into the derivative of x square. Derivative of x square is 2x. So it will be f dash of x square into the derivative of x square, which is 2x minus 6 into derivative of f of 4x square. Derivative of f of 4x square is f dash of 4x square into f dash of 4x square into the derivative of 4x square. Derivative of 4x square is 8x plus 5 into, here we have f of 7x square. Derivative of f of 7x square is f dash of 7x square into the derivative of 7x square. Derivative of 7x square is 14x. Okay? Now, in the denominator, I will take 2x as a common factor. I will take 2x as a common factor and I will cancel that with this 2x of the numerator. Okay, so after taking 2x as common and after cancelling it, we will be left with 1 in the numerator. In the denominator, I have cancelled 2x. So f dash of x square is there. Minus here, I have cancelled 2x. So 4 is remaining here. 4 into 6, that is 24. So we will get minus 24 into f dash of 4x square plus, here we have cancelled 2x, means 7 is remaining here. That 7 into this 5 will give us 35. 5 into 7, 35. 35 f dash of 7x square. Okay, now we are left with this. Now you apply the limit as x tends to 0. So when I apply the limit as x tends to 0, we'll have 1 by f dash of 0 minus 24 into f dash of 0 plus 35 into f dash of 0. I am putting x as 0. I am applying the limit now. F dash of 0 minus 24 into f dash of 0 plus 35 into f dash of 0. Together what do you get? 35 plus 1. 36 f dash of 0 minus 24. 36 minus 24 is equal to 12. So we get 1 by 12 into f dash of 0. Okay? So on simplification we get 1 by 12 into f dash of 0. What is f dash of 0? In the question they have given that f dash of 0 is equal to 3. So 12 into 3 will give you 36. Hence the answer is 1 by 36. 1 by 36, which is the first option. Okay, let's move to the next question. 74. If the function defined by f of x equal to sin 3 into x minus p divided by sin 2 into x minus p for x not equal to p is continuous at x equal to p, then f of p is. Okay, so that function is defined like this. F of x is equal to sine 3 into x minus p divided by sine 2 into x minus p when x not equal to p, and it is okay. What happens at x equal to p? Not given, so let me take it as k when x equal to p. F of x is sine of 3 into x minus p by sine 2 into x minus p for x not equal to p, and for x equal to p I have taken it as k. Now that k only we have to find out. It is given that the function is continuous at x equal to p. Since the function is continuous at x equal to p, I can write limit extends to p, f of x is equal to f of p. In other words, sine 3 into x minus p divided by sine 2 into x minus p is equal to f of p. Okay, since f of x is continuous at x equal to p, limit extends to p, f of x is equal to f of p. Okay, so now I would like to apply the limit here. Directly if I apply the limit, I am going to get 0 by 0, p minus p 0, sine 0 is 0, denominator also 0, 0 by 0. So it's an indeterminate form. You can use L-Hospital's rule, or else directly also you can write 3 by 2. Or I will explain in detail. I divide by 3 into x minus p. Sine 3 into x minus p divided by 3 into x minus p. Since I have divided it, I will multiply. To compensate it, I am multiplying by 3 into x minus p. Similarly, in the denominator, sine of 2 into x minus p divided by 2 into x minus p into 2 into x minus p. Now, as x tends to p, x minus p will tend to 0. So, this is as good as sin theta by theta as theta tends to 0. As theta tends to 0, sin theta by theta equal to 1. So, that formula I am using here also. And here what happens? X minus p gets cancelled. This is 1, this is 1. So, the answer is 3 by 2. That's equal to 3 by 2. That is equal to f of p. So, f of p is equal to 3 by 2. First option. Okay, then if f from R to R defined by f of x is equal to x plus 2 by x square plus 3x plus 2 wherever x belongs to R minus 1 comma minus 2. That is, whenever x is a real number but not equal to minus 1 and not equal to minus 2. Set of all real numbers except minus 1 and minus 2. Except at those 2 points, f of x is defined as x plus 2 by x square plus 3x plus 2. At minus 2, it is defined as minus 1. At minus 1, it is defined as 0. Then the question is, where it is continuous? Okay. So, f of x is equal to x plus 2 divided by x square plus 3x plus 2 when x belongs to R minus 1 minus 2. It is minus 1 if x is equal to minus 2, and it is 0 if x is equal to minus 2. Okay. See, at these 2 points, what happens? That's what we have to check. Everywhere else it is obviously continuous. Okay. First, understand how this function is defined. Except at minus 1 and except at minus 2, everywhere else the function is defined as f of x is equal to x plus 2 divided by x square plus 3x plus 2. Okay, everywhere else it is defined as this. So, now, everywhere else, let us say, numerator is a polynomial, denominator is also a polynomial. So, as we know, every polynomial function is continuous. So, numerator is continuous, denominator is continuous means this expression is also continuous, provided denominator is non-zero. When is the denominator 0? And denominator x square plus 3x plus 2 is equal to 0. On factorization, you get x plus 1 into x plus 2 is equal to 0. That means at x equal to minus 1 and at x equal to minus 2, denominator is 0. But we are not talking about minus 1 and minus 2. Now, I am looking at all real numbers except the minus 1 and minus 2. Okay. So, everywhere else the function is defined like this. So, everywhere else it is continuous. Right? No doubt about that. The only doubt that we have now, or only 2 doubts we have now, is whether the function is continuous at minus 1 or not, and whether the function is continuous at minus 2 or not. So we need to check the continuity at those 2 points. Everywhere else it is continuous, no doubt. Okay. The only doubt we have is at -1 and at -2. Okay. So at -1 and at -2, what happens? Let us see. Okay. First I would like to test the continuity at x equal to -1. So I'll go for this. Limit x tends to -1 f of x. As x approaches -1, see when x is equal to -1, the function is defined as 0. When x is equal to -2, the function is defined as -1. Everywhere else, the function is defined as x plus 2 by x square plus 3x plus 2. So when I write x approaches -1, f of x, this f of x, we should write this function x plus 2 by x square plus 3x plus 2, because when I say x is approaching -1, its meaning is x is coming closer and closer to -1, not equal to -1. It's very close to -1, right? So there at -1 only it is defined as 0, everywhere else is defined like this. Okay. Now I'll factorize this. On factorization, this will give you x plus 1 and x plus 2. X plus 2, x plus 2 gets cancelled. So you have limit x tends to -1, 1 by x plus 1. 1 by x plus 1. Limit x tends to -1, 1 by x plus 1. This limit does not exist. Okay. So limit does not exist means then can it be continuous at that point? Answer is no. Okay. So it is clear that the function is discontinuous at -1. Right. Now we need to check the continuity at -2. So at -1 it is discontinuous. At -2 what happens? Let us observe. Limit x tends to -2 f of x. That's equal to limit x tends to -2 f of x. F of x is x plus 2 by x square plus 3x plus 2. On factorization, this will give you x plus 1 and x plus 2. X plus 2 gets cancelled. So you have limit x tends to -2, 1 by x plus 1. Apply the limit now. -2 plus 1 is -1. This is equal to -2. So limit x tends to -2 f of x to -1. What about f of -2? F of -2 is also equal to -1. Limit value is equal to -1 and the functional value is also equal to -1. Therefore, the function is continuous at this point. So from this we observe that it is discontinuous only at -1. Everywhere else it is continuous. So the answer is, question is where it is continuous. Okay. So we have found that at -1 it is discontinuous, everywhere else it is continuous. So everywhere else means set of all real numbers except -1. Okay. Next. 79th question. F of x equal to x square by mod x when x not equal to 0. And it is f of 0 is equal to 0. Then what happens to f of x? Is it discontinuous? It's printed as discontinuous, make it as discontinuous. F of x is discontinuous everywhere. F of x is everywhere. Okay, that y is also missing. We just add. F of x is continuous everywhere. F dash of x, this is f dash of x, exists in open interval -1 to 1, and f dash of x exists in open interval -2 to 2. I'll rewrite the given function in this way. F of x equal to, we have x square by mod x. I can write x square as mod x whole square divided by mod x. That's equal to mod x. So we are left with f of x equal to mod x. Okay, f of x equal to mod x. You know the graph also. F of x is equal to mod x. Where it is continuous? It is continuous everywhere. Where it is not differentiable? At 0, it is not differentiable. And 0 is present in these two intervals. So if you write f dash of x exists in this interval, you are wrong, because at 0, it is not differentiable. So the answer is f of x is continuous everywhere, which is the second option. Okay. See, if we can identify like this, that x square can also be written as mod x whole square, then okay, well and good, directly we will get the answer. If you think, sir, if I don't identify, then what should I do? I'll tell you what to do. Okay. See, f of x equal to, we have x square by mod x, right? I'll split it into 2 cases, or 3 cases rather. If x less than 0, x greater than x equal to 0, and x less than greater than 0. Okay. I'll consider 3 cases, when x is negative, when x is 0, and when x is positive. Okay. So f of x equal to, first when x is negative, how do you define mod x? whenever x is negative, mod x is defined as minus x. So x square divided by minus x will give you minus x if x is less than 0. At 0, they have only given f of 0 is 0, no doubt 0 if x equal to 0. When x is positive, what happens to mod x? Whenever x is positive, mod x is defined as x. X square by x will give you x if x is greater than 0. F of x is equal to minus x when x is negative, 0 when x is 0, and x when x is positive. This is nothing but mod x. F of x is equal to mod x. As soon as you see mod x, immediately this graph should come to your mind, and you must also identify that it is continuous everywhere and not differentiable at 0. Okay, so the answer is second option. Then the function f of x is equal to x plus x by 1 plus mod x is differentiable at everywhere except at x equal to plus or minus 1, except at x equal to 0, except at x equal to 0 or x equal to plus or minus 1. Okay. So, to test the differentiability of your function, you know the method, that is. So, let us say let f of x be any function, let a be a point in its domain. I want to know whether f is differentiable or not at x equal to a. Then what I should do is, I should find out this limit. Limit extends to a f of x minus f of a divided by x minus a. Check whether this limit exists or not. If this limit exists, then we say that the function is differentiable at that point, and this expression, this value is called, the limiting value of this is called f dash of a, the derivative of f at x equal to a. Okay, so when I say limit exists means left hand limit should exist and right hand limit should also exist. Here we call them as left hand derivative and right hand derivative. So left hand derivative means limit extends to a minus f of x minus f of a divided by x minus a. This should exist. Right hand derivative means limit extends to a plus f of x minus f of a divided by x minus a. This should exist. These two should exist and they should be equal. These two should exist and they should be equal. Then we say that the function is differentiable at x is equal to a. Theoretically, this is how you do it. But when it comes to competitive exams, I'll give you another method with which you can directly solve. Okay. So the other method is directly you differentiate it and substitute that point. So you will find the derivative and you substitute that point. If the function is defined at that point, if your f dash is defined at that point, that means the function is differentiable at that point. If f dash of x does not exist at that point, then we can say the function is not differentiable at that point. Okay. So what I do is, I will consider three cases here by looking at the options. I will consider 0, 1 and minus 1. First I will go with 1 and minus 1, then I will come back to 0. 0 is slightly complicated here because of the presence of mod x. Okay. So first I would like to see what happens at x equal to 1. For that, I will see f of x. What is f of x? F of x is equal to x by 1 plus mod x, right? Mod x, I am looking at x equal to 1. When I say I am looking at x equal to 1, I am looking at the neighborhood of 1. Okay? In the neighborhood of 1, how do you define mod x? As you know, mod x, whenever x is positive, mod x is equal to x. Whenever x is negative, mod x is equal to minus x. In the neighborhood of 1, what happens to mod x? Mod x will be equal to x. So you get x by 1 plus x. This is f of x at x equal to 1. Now what I will do is, I will differentiate it and put x equal to 1. So try to get f dash of 1. Check whether it exists or not. Okay? So differentiate it f dash of x. You know the quotient rule. X plus 1 whole square in the denominator. Numerator x plus 1 into derivative x is 1. Minus x into the derivative 1 plus x, which is 1. So x plus 1 minus x divided by x plus 1 whole square. X gets cancelled. 1 by x plus 1 whole square. This is our f dash of x. What is f dash of 1? That's equal to 1 plus 1 by 2. 2 square is 4. 1 by 4. It is well defined. F dash of x exists at x equal to 1. That means the function is differentiable at x equal to 1. Now I go to minus 1. So it's clear that f is differentiable at 1. Now let us see whether it is differentiable or not at minus 1. Okay, I'll consider x equal to minus 1. X equal to minus 1 means I am talking about this point. Okay, and I am talking about the neighborhood of minus 1. In the neighborhood of minus 1, how do you define mod x? Mod x, as we know, mod x is equal to x when x is positive and minus x when x is negative. Now I am talking about the neighborhood of minus 1. Minus 1 is negative, so in its neighborhood also x is negative. X is negative means there mod x is defined as minus x. So that function f of x will be equal to x divided by 1 minus x. Okay. Now you find out f dash of x. F dash of x is equal to, in the denominator, 1 minus x whole square. In the numerator, 1 minus x into derivative x, which is 1. Minus x into derivative 1 minus x, which is minus 1. That's equal to 1 minus x plus x divided by 1 minus x whole square. X gets cancelled. F dash of x is equal to 1 by 1 minus x whole square. We are talking about x equal to minus 1. Put x equal to minus 1 here. We get 1 by 4. F dash of minus 1 is equal to 1 by 4. That means the function is differentiable at x equal to 1 also. Okay. So the only doubt that we have now is at a 0. At a 0. Mod x and 0. Okay. So in general, mod x, we know it is not differentiable at x equal to 0. But now let us check what happens. Now I am talking about differentiability at x equal to 0. So this is 0. If I consider the neighborhood of 0, in the left neighborhood it is negative, in the right neighborhood it is positive. In the left neighborhood of 0, mod x is defined as minus x, and in the right neighborhood of 0, mod x is defined as plus x. So we need to go for left hand derivative and right hand derivative separately in this case. Okay. So for left hand derivative, what it is nothing but limit x tends to 0 minus f of x minus f of 0 divided by x minus 0. This is actual method. Direct method, what I do is left hand derivative at, that is f dash of 0, f dash of x first I will find out, or f of x. For left hand derivative, what is f of x? X by 1 minus x, because left hand derivative means x is approaching 0 from left side. When x approaches 0 from left side, mod x is negative, therefore mod x is defined as minus x. Now differentiate. F dash of x is equal to denominator 1 minus x whole square, numerator 1 minus x into derivative of x, that is 1, minus x into minus 1. This on simplification will give you 1 by 1 minus x whole square. This is f dash of x, left hand derivative. Now f dash of 0 minus. F dash of 0 minus means left hand derivative of f at x equal to 0. Okay. So what happens then? We get 1. Put x equal to 0, we get 1. So left hand derivative is 1. Let us see what happens to right hand derivative. Okay. At x equal to 0, left hand derivative is equal to 1. Now I am interested in knowing what is right hand derivative. For right hand derivative, this should be x is approaching 0 from the right side. This is the actual method. Or else, now if I consider f of x as x by 1 plus x, then what happens? F dash of x is equal to differentiate 1 plus x whole square, numerator is 1 plus x into derivative of x, which is 1 minus x into 1. That will give you 1 by 1 plus x whole square. This is f dash of x. Now f dash of 0 plus. That means f dash of 0 plus means that right hand derivative of f of x at x equal to 0. Put x equal to 0, that will give you 1. Left hand derivative is 1, right hand derivative is 1. Hence the function is differentiable at 1 at 0 also. So which means it suggests that function is differentiable everywhere. Okay? Then next question. 82. The function f of x is equal to 1 minus x if x is less than 1, 1 minus x into 2 minus x if x is less than or equal to 1, greater than or equal to 1, but less than or equal to 2. and 3 minus x if x is greater than 2. Is differentiable at 1, differentiable at 2, differentiable at 1 and 2, not differentiable either at 1 or at 2. Okay. Before testing differentiability, first of all we have to check continuity. If the function is not continuous at a particular point, then it cannot be differentiable at that point. As we know, every differentiable function is continuous. Okay? But if it is not continuous, then clearly it cannot be differentiable. Okay. So now let us consider this. F of x is equal to 1 minus x if x is less than 1. 1 minus x into 2 minus x. I will multiply that. I am getting 2 minus x minus 2x, that is 2 minus 3x plus x square if x is greater than or equal to 1, less than or equal to 2. 3 minus x if x is greater than 2. Okay. First I will test continuity. Continuity at x equal to 1. Okay. So for that, left hand derivative, directly put x equal to 1 here, you get 0. Right hand derivative, put x equal to 1 in this, because when x is greater than or equal to 1, function is defined. This is a shortcut, I think I have explained it earlier. Yes, I have. Okay. So left hand derivative, left hand limit, this is not left hand derivative, this is left hand limit. I am testing the continuity at x equal to 0, at x equal to 1. Okay. I want to test the continuity at x equal to 0, 1. To test the continuity, directly you put x equal to 1 at that point. So here for left hand limit, this is what I have to consider. Put x equal to 1 here, 1 minus 1, 0. Then for right hand limit, this is what I have to consider. For at x equal to 1, the right hand limit I am finding. Put x equal to 1 here, that will give you 2 minus 3 plus 1. 2 minus 3 plus 1 is equal to 0. So at 1, left hand limit is 0, right hand limit is also 0. Okay. Therefore, we can say that function is continuous at 1. Because at 1, f of 1 will also give you this. So left hand limit is equal to right hand limit is equal to function value. Therefore, the function is continuous at x equal to 1. Then I want to test the continuity at x equal to 2. Now left hand at x equal to 2. So for left hand limit, this is what I have to consider. For 2, left hand limit, this is what I have to consider. Put x equal to 2 here. 2 minus x plus 4. 2 minus x plus 4, that will give you 0. Right hand limit is equal to, now right hand limit, put x equal to 2 here, 3 minus 2, which is 1. Left hand limit is 0, right hand limit is 1. The limit does not exist. Therefore, the function is discontinuous at x equal to 2. So if it is discontinuous at 2, clearly it is not differentiable at 2. Okay. So no need to check whether it is differentiable or not at x equal to 2. Okay. So clearly at 2 it is not differentiable. We only need to check what happens at 1. Okay, see, from this we have seen that f of x is continuous at x equal to 1 and discontinuous at x equal to 2. Discontinuous directly implies that it is non-differentiable also. So, but continuity does not imply differentiability. Differentiability implies continuity. I mean, if a function is differentiable, then it must be continuous. But if a function is continuous, then that function may or may not be differentiable. Okay. So from that we can say if a function is discontinuous at a point, then clearly it is non-differentiable at that point. Okay. So now the function is continuous at 1, we have seen. Let us test the differentiability at 1. For that, what we do is, see, I will tell you how to find out f dash of x. You directly differentiate this for left hand derivative. Okay. Left hand limit, this directly we substitute the value. For left hand derivative, directly you differentiate. What do you get? Minus 1. Then for this, you differentiate this. What do you get on differentiation? Minus 3 plus 2x. And this we are not interested in, because at 2 we already know it is not differential, so don't worry about it. Okay. Left hand derivative, you differentiate this. Okay. Then where we are finding at 1. Right? So this is at like x less than 1, this is x greater than 1. At 1, what happens? We don't know. So put x equal to 1. When I put x equal to 1, here it is minus 1 itself. Here if I put x equal to 1, what I am going to get? Minus 3 plus 2. Minus 3 plus 2 will give you minus 1. Okay. So from this we observe that left hand derivative is minus 1, right hand derivative is also minus 1. Hence the function is differentiable at x equal to 1. So the answer is differentiable at x equal to 1. Okay, this is one way of solving this problem. There is easier way, shortcut, or the actual method is left hand derivative. We should use this. Limit x tends to 1 minus f of x minus f of 1 divided by x minus 1. That's equal to limit x tends to 1 from left side. F of x, when x approaches 1 from left side, f of x is defined as 1 minus x. Minus f of 1, what happens to f of 1? 0 divided by x minus 1. Here 1 minus x minus 1 gets cancelled, we will have minus 1. Left hand derivative is minus 1. Now I want to find out right hand derivative. Right hand derivative is equal to limit x tends to 1 plus f of x minus f of 1 divided by x minus 1. Okay, that's equal to limit x tends to 1 f of x is 2 minus 3x plus x square. That cancels it as 1 minus x into 2 minus x. Minus f of 1, what is f of 1? 0 divided by, in the denominator, x minus 1. That's equal to, what happens now? Numerator is 1 minus x into 2 minus x. Denominator is x minus 1. If I cancel 1 minus x minus 1 gets cancelled, minus 1 will remain. Minus 1 into 2 minus x. It will become x minus 2. Right? So I will write here because not enough space available. Limit x tends to 1. On simplification, you will get x minus 2. Right? 1 minus x minus 1 gets cancelled, minus 1 will remain. Minus 1 into 2 minus x, that will give you x minus 2. Apply limit 1 minus 2, that's equal to minus 1. Okay, so we observe that left hand derivative is minus 1 and right hand derivative is also minus 1. Hence the function is differentiable at x equal to 1. This is the actual method. Earlier I gave you the shortcut, directly you differentiate it, put that value, we can directly get the answer. Okay, then let's go to the next question now. 85. That f of x is equal to 1 plus cube root of x minus 1 whole square. That are the set of all the points at which f of x is differentiable is. Okay. The question is where this function f of x is differentiable, they are asking. So that f of x I will write as 1 plus cube root of x minus 1 whole square can be written as x minus 1 whole power 2 by 3. Okay. See, instead of taking 1, 0, minus 1, 2, 3, 4, etc. and checking whether it is differentiable or not at that point, what I would suggest is, first you find out f dash of x, whatever may be the given function. Find out f dash of x and then by looking at that f dash of x, you identify where it does not exist. Okay? So let us differentiate this. F dash of x, that's equal to, here f1 is 0. 2 by 3 into x minus 1 to the power 2 by 3 minus 1. 2 by 3 minus 1 will give you minus 1 by 3 into the derivative x minus 1 which is 1. So that's equal to 2 by 3 into x minus 1 to the power 1 by 3. Here minus 1 by 3, I will take it to denominator 1 by 3. This is our f dash of x. Now you observe, numerator is a constant, denominator has some variable here. This when it does not exist. This does not exist whenever the denominator is 0. So when the denominator will be 0, this denominator will be 0 when x equal to 1. So it suggests that f dash of x does not exist at x equal to 1. Okay? At 1 the function is not differentiable, everywhere else it is differentiable. So the answer is set of all reals except 1 r minus 1. Second option. Then the function represented by the following graph is. Okay, so observe that this graph is very similar to the graph of mod x, but with the difference that, see, I think I have already told you, this is the graph of, this is the graph of mod x, which touches x axis at 0. This is the graph of mod x minus 1. This is the graph of mod x minus 2. This is the graph of mod x minus 3. This is the graph of modulus of x plus 1. Okay? Say, this is mod x, this is mod of x minus 1, this is mod of x minus 2, this is mod of x minus 3, this is mod of x plus 1, etc. So in general, mod x minus a has a sharp edge whenever it touches x-axis. So it touches x-axis at 3, mod x minus 3, mod x minus 2 touches x-axis at 2, mod x minus 1 touches x-axis at 1, mod x touches x-axis at 0, mod of x plus 1 touches x-axis at minus 1. So that function, whenever it touches x-axis, at that point it is not differentiable. It is continuous everywhere. Whenever it touches x-axis, because at x-axis there is a sharp edge. So here also at 1, at x-axis there is a sharp edge. So that graph, it is nothing but the graph of modulus of x minus 1. Okay? It is continuous everywhere, but not differentiable at x equal to 1. Continuous but not differentiable at x equal to 1. First option is the answer. Okay? In general, mod x minus a is continuous everywhere, but not differentiable at x equal to a. So using that rule, I can say that the function is continuous at 1, but not differentiable at 1. Okay, next. The value of k, which makes the function defined by f of x is equal to sin 1 by x when x not equal to 0, k if x equal to 0 is continuous at x equal to 0. Okay, f of x is equal to sin of 1 by x when x not equal to 0 and k if x equal to 0. This is continuous at x equal to 0, they have given. So that means limit extends to 0 f of x must be equal to f of 0 by the definition of continuity. So limit extends to 0 f of x. In place of f of x, I will substitute sin 1 by x, that should be equal to f of 0. What is the value of this limit? This limit does not exist, sin 1 by x. We only know that it lies somewhere between minus 1 and 1. It is a finite value between minus 1 and 1, but we don't know what is its exact value. So this limit does not exist. Hence, there is no value of k which makes this function as f of 0 is nothing but k. There is no value of k. Hence, none of these is the answer. 89th question. The set of points where the function f given by f of x will mod x minus 3 into cos x is differentiable is. Observe here, f of x is equal to mod x minus 3 into cos x. Okay, it's a product of two functions, mod x minus 3 and cos x. Cos x, as we know, it is differentiable everywhere. Okay, throughout its domain it is differentiable. And so now it only depends on mod x minus 3. Mod x minus 3, where it is not differentiable? It is not differentiable at 3. So this function is not differentiable at 3. Everywhere else it is differentiable. So the answer is set of all reals except 3, second option. Okay, 90th question. Limit extends to 0, x e power x minus sin x by x is equal to. So limit extends to 0, x e power x minus sin x divided by x. If I directly apply the limit, I am getting 0 by 0. I will split this into two terms. First term, x e power x divided by x, x gets cancelled, e power x. Second term, sin x by x. Apply the limit as extends to 0. When x approaches 0, e power 0 is 1. Minus as extends to 0, sin x by x is also equal to 1. 1 minus 1 is 0. Third option is the answer. Okay. 92nd question. Limit theta tends to 0. 1 minus cos 4 theta. 1 minus cos 4 theta divided by 1 minus cos 6 theta. Directly I can write the answer m square by n square. M square by n square. You know this formula. Limit theta tends to 0. 1 minus cos m theta divided by 1 minus cos n theta is equal to m square by n square. Remember this formula. So if you know that formula, answer is 16 by 36. 4 4s are 4 9s are. 4 by 9 is the answer. Okay, understood? Okay, fine. If you have understood, well and good. If not, I know I am sure there are few students who don't know that formula. If you don't know the formula, then also no need to worry, you can get the answer easily. If I directly apply the limit, I am getting 1 minus cos 0. Cos 0 is 1, 1 minus 1 is 0. Denominator also 1 minus 1, 0 by 0. And indeterminate form, go for L-Hospital's rule. So when I differentiate this, I am going to get sin 4 theta into 4. divided by derivative cos minus cos 6 theta is sin 6 theta into 6. As you know, sin 4 theta by 6 theta, sin 6 theta will give you 4 by 6 into another 4 by 6. 4 by 6 into 4 by 6, that's equal to 16 by 36, which is equal to 4 by 9. That's the answer. 4 by 9, third option. 94th question. If f of x is equal to root of 1 plus kx minus root of 1 minus kx by x, when x is between minus 1 and 0, and it is 2x plus 1 by x minus 1 when x is between 0 and 1, is continuous at x equals 0, then the value of k is. So they have given that function is continuous at x equals 0, therefore I can write a limit extends to 0 minus f of x is equal to limit extends to 0 plus f of x. Left hand limit must be equal to right hand limit must be equal to the functional value. Must be equal to the functional value f of 0. Okay? So now limit extends to 0 minus. When x approaches 0 from left side, the function is defined as root of 1 plus kx minus root of 1 minus kx divided by x. Okay? That's equal to limit extends to 0 from right side, that is 2x plus 1 by x minus 1. That's equal to f of 0. At 0, we directly put x equal to 0 here, that will give you 1 by minus 1, which is minus 1. Okay. Here if I directly apply the limit, we get a root 1, which is 1, minus root 1, that is also 1. 1 minus 1 is 0. Numerator is 0, denominator is also 0. 0 by 0, I go for L Hospital's rule. That will give you, differentiate this, 1 by 2 root of 1 plus kx into k minus, the derivative of this is 1 by 2 root of 1 minus kx into minus k. Denominator 1, derivative of x is 1. That's equal to, here if I apply the limit, there also I am going to get minus 1 itself. Right? Put x as 0, 1 divided by minus 1. Minus 1. Now if I apply the limit as x tends to 0, this will give you k by 2. But minus and minus plus, there it will be k by 2 equal to minus 1. K by 2 plus k by 2 is equal to k, and k equal to minus 1. Unfortunately, we don't have the option. Okay, it's a typing mistake among these two. One of them should be k equal to minus 1. I think it is the second option. Anyway, k equal to minus 1 is the right answer. Okay, next. If f of x is equal to log x by x minus 1, when x not equal to 1, and k if x is equal to 1, it should be if x equal to 1, then don't think that ix equal to 1, it should be if x equal to 1, is continuous, not continuous at 1, it is continuous at x equal to 1, then the value of k is. So given that the function is continuous at x equal to 1, we can directly write limit extends to 1 f of x is equal to f of 1. So limit extends to 1 f of x. F of x is log x divided by x minus 1. That's equal to f of 1. F of 1 is k. Right. If I directly apply the limit, I am getting log 1. Log 1 is 0. Denominator also 1 minus 1 is 0. 0 by 0. Use L Hospital's rule. Derivative log x is 1 by x. Derivative of x minus 1 is 1. Is equal to k. Apply the limit as x tends to 1. K is equal to 1, second option. Okay, that's it. So with that we have come to the end of limits and continuity. In the next class I'll start differentiation. Okay, differentiation, CAT problems. So I advise you to go through your in PUC whatever I have taught you on differentiation. You just go through that notes, go through it, and then understanding will be easy.